Show by the principle of mathematical induction that for all n belonging to the set of natural numbers, the sum of n terms of the series whose nth term is given by tangent inverse of 1 over 2n squared, that sum is given by tangent inverse of 2n plus 1 minus pi over 4. Okay, let us begin. First, what we'll do, we're going to rewrite the series. So let us suppose that the first term is given by a1. Then we have the next term, which is a2, followed by the third term, this is a3. So this goes all the way up to the nth term, and the nth term is given as tangent inverse of 1 over 2 times n squared. And when we sum this series, the result is also given to us. The result is tangent inverse of 2 times n plus 1 minus pi over 4. So this much of information is given to us. Now we do not have to show here that the sum of this series adds up to give us tangent inverse of 2n plus 1 minus pi over 4. Rather, we have to show that this statement is going to be true for any natural number that we pick up. So what we'll do, we'll convert this into a mathematical statement. For this, we will suppose that let Pn be a statement. It's a mathematical statement such that we have this series. So we have successfully converted it into a mathematical statement. We'll have to show that the statement P of n is valid for all n belonging to the set of natural number by using the principle of mathematical induction. So, okay. Let us now begin. So here what we'll do, we will first check whether if the statement holds true if we consider n equals to 1. So for n equals to 1, we have the statement P of 1. Okay. So P of 1, what we'll do, we're going to take the nth term which is given to us and we'll replace that n value with 1. So that's going to be the value tangent inverse of 1 over 2. So tangent inverse of half. This is going to be equals to, on the right hand side, we have tangent inverse of 2n plus 1. So when you substitute n with 1, so we have 2 plus 1, which is simply going to be 3. We have tangent inverse of 3 minus pi over 4. However, we have to further simplify to make sure that the left hand side equals to right hand side. So let's work with the right hand side. So here we have tangent inverse of 3 minus the second term, which is pi over 4. But pi over 4 can be also expressed as tangent inverse of 1. Now what we have the difference of two tangent function. There is a standard formula for combining them. So if we have tangent inverse of x minus tangent inverse of y, this is simply given by the inverse tangent of x minus y divided by 1 plus x times y. Which means in our case, x is going to be denoted by 3 and y will be 1, such that we have the inverse tangent of x minus y. So that means 3 minus 1 divided by 1 plus 3 multiplied to 1. So this is going to be equals to tangent inverse of, so 3 minus 1, that's 2 in the numerator, and 1 plus 3, that's 4 in the denominator. So 2 over 4 is also 1 over 2. So here we have shown that the left hand side equals to right hand side. This simply tells us that the statement P of 1, this is a true statement. So we have successfully verified for n equals to 1, the statement P of n is valid. However, we also need to check whether if it is true for other natural numbers or not. So let's consider another natural number m. So let n be equals to m. In essence, what we are saying that the statement P of m, which is such that we have a1 plus a2, the second term, going all the way up to the last term, which is tangent inverse of 1 over 2. But this time we're going to replace this n with m. We have m squared. This is going to be equals to tangent inverse of 2 times m plus 1 minus pi over 4. So this is our statement P of m, and we are assuming this is a true statement. This is an assumption. So let's call this statement number 3. Using this statement, our goal will be to verify that if we consider the next consecutive natural number to that of m, which is simply m plus 1, we have to verify that P of m plus 1 is also true. That this is also a true statement provided P of m is already true. Now what is P of m plus 1? If we write it down, P of m plus 1, this statement is going to be, we have the first term added to the second term, added to the third term, going all the way up to the term tangent inverse of 1 over 2m squared. However, this is the second last term. This is not the last term. To get the last term, what we'll have to do, we have to replace m with m plus 1. Now that means we have tangent inverse of 1 over 2 times m plus 1 whole squared. So this is going to be our last term, and we have to show that this equals to a tangent inverse of, so if we replace m with m plus 1, we're going to get 2 times m plus 3 minus pi over 4. So our goal will be to verify that this is also a true statement. So let's call it statement number 4 for the time being. Now what we'll do, we will verify this by considering the left hand side. So now let us consider only the left hand side of the statement p plus 1. So here we have e1, the first term, added to the second term. This goes all the way up to the second last term, which is given by tangent inverse of 1 over 2 times m squared, added to tangent inverse of 1 over 2 times m plus 1 whole squared. Fine. Now, luckily for us, if we consider the first term added all the way up to the second last term, what we can do, we can simply replace it with the right hand side of statement number 2, because that is a true statement. So that means we have tangent inverse of 2 times m plus 1 minus pi over 4, added to tangent inverse of 1 over 2 multiplied to m plus 1 whole squared. Fine. Okay. So we were going to combine these two terms, and we'll have to show this is equivalent to tangent inverse of 2m plus 3 minus pi over 4. So fine. So what we'll do, we'll take the first term, which is tangent inverse of 2 times m plus 1, and we're going to add the third term, which is tangent inverse of 1 over 2 times m plus 1 whole squared. Then we have the second term, but we're going to keep it as the third term, minus pi over 4, because we need a negative pi over 4. So all we have to do is combine the first term and the second term. Now how do we combine the first term and the second term? So here again we are going to use the formula. Now this time, earlier we had tangent inverse of x minus tangent inverse of y, but this time we have tangent inverse of x added to tangent inverse of y. Now this is going to be, the sum is going to be equals to the tangent inverse of x plus y divided by 1 minus xy, which means that when we combine, we are going to get tangent inverse of, we have 2 times m plus 1. This is going to get added to 1 over 2 times m plus 1 whole square, whole divided by 1 minus the product of 2m plus 1 and 1 over 2 times m plus 1 whole square. Fine. So we'll have to simplify this, and we have the second term, which is negative pi over 4. Okay. Now further simplification is going to give us the inverse tangent of, so in the numerator we're going to have 2 times m plus 1 multiplied to 2 times m plus 1 whole square, added to 1, whole divided by, and the denominator we have 2 multiplied to m plus 1 whole square minus 2 times m plus 1, this is done, minus pi over 4. Now when we simplify the numerator and the denominator separately, in the numerator portion we are going to get 4m cubed added to 10m squared added to 8m plus 3 whole divided by, so we have 2 times m squared plus 2 times m added to 1. Okay, next we also have negative pi over 4. Now I'm leaving the next part as an exercise for you to try out. If we take the numerator, which is a cubic expression, and we divide it by the denominator, so that's we can perform a long division here. That's going to leave us with the remainder of 2 times m plus 3 minus pi over 4, and this is exactly the expression on the right hand side. We can verify that. So on the right hand side, we need a tangent inverse of 2m plus 3 minus pi over 4. So here what we have done, we have shown here that the left hand side equals the right hand side. If the left hand side equals the right hand side, we can say that the statement p of m plus 1, which we considered, this is a true statement. In other words, we considered the statement p of m, so we suppose that that is a true statement. So if this is a true statement, it simply means that p of m plus 1 is also true. That is what we have done so far. Now that we have shown that p of m plus 1 is true, provided p of m is true, hence we can say by the principle of mathematical induction, we can say that our statement, the original statement p of n, that is going to be a true statement. That is going to be true for all values of n belonging to the set of natural numbers. That means any natural number that we pick up, original statement p of n, where p of n is given by the statement number 1, this is going to be a valid statement, hence proof.